Biggest trends. I mean, I think that we've always had the same challenges. I think since the beginning. So the question is, what are we doing to fix those challenges, right? And one of the challenges that's always been sort of a hurdle for us is just speed, right? So I think the one of the biggest trends we have right now is just GPU computing, right? And some of the codes that we have had for decades is now getting completely rewritten from scratch, and it's necessary. It's time, right? The bottom layer, the hardware layer, is having a complete technology shift, right? Going from sort of the previous constraints of Moore's law and transistor density on CPUs to what looks like NVIDIA sort of cracking the code on that, right, and providing an unbelievable amount of computing density in their GPU structure. So, Fluid's GPU solving right now is some of the craziest like steps in speed that we've ever seen, to be honest. We were benchmarking stuff a few months ago that was 20, 30, 50x speed up. We've never seen a jump like that. Even when we started getting to parallel processing, we didn't see that level. Maybe it was 2x, 3x something. So that GPU solving is incredible. We're starting to see that come into the finite element methods. With some of the code inside of ANSYS, for example, starting to get rewritten for the first time since the company was founded in the 70s. So we have some pretty interesting innovations happening on the GPU side and the speed side. The other is, I think, on the predictability, right? And this kind of brings us back into our favorite topic, Yusuf, of AI and ML. But what's the reason that we do simulation? It's to kind of predict the future. And so a lot of times our goal for creating a physics model is for it to be able to predict something that we can't easily prototype and test. And so we're seeing a lot of, I think, trends towards adopting ML and AI, not necessarily innovation. There's innovation happening, sure, but some of these tools have been around now for over 10 years, right? And so I think the adoption side is starting to build some momentum, right? And we're starting to learn how to work alongside these tools, which is different than maybe even just a year or two ago. So those are two big ones. I think the third one too is interoperability. Multiphysics is the name of the game. We live in a multiphysics world. So you don't, a lot of times I'm not going to go into FEA with an FEA only mindset, a structures only mindset. My boundary conditions for a structures model is going to imply other physics, right? Heat transfer rate is implying airflow, right? For example. And so I might simplify a dynamic problem to static or quasi-static. So, multiphysics nowadays, we're able to hook in across physics. So I can hook in my structures to my fluids. I can hook in my electromagnetics to my thermal, right? I don't have to make these overly conservative or otherwise assumptions on boundary conditions. So for me, the big three trends are speed with GPU, predictability with AI ML, and breaking down barriers with multiphysics.